there's no longer enough energy left in the light to sustain photosynthesis. And so, even though there's vast ecosystems out there of water, vast biomes, full of water, only the very surface of these large ecosystems have enough light to sustain photosynthesis. So productivity will, by definition, be limited to that region of aquatic ecosystems that have enough light to allow for photosynthesis. But, unlike terrestrial ecosystems, aquatic ecosystems lack soil. So when something dies in the ocean, it sinks. And it very quickly sinks so deep that it's in water that doesn't have enough light to sustain photosynthesis. So by the time that dead material or that waste is broken down and recycled into a form that can be reused for photosynthesis, it's now too deep and in water that doesn't have enough light to allow it to be used. So these nutrients tend to build up and accumulate in deep, dark water. And so there's a disconnect. Where you have enough light, you don't have enough nutrients. Where you have enough nutrients, you don't have enough light. And so productivity is going to be limited in aquatic ecosystems to those regions where there's enough nutrients and enough light to sustain photosynthesis. So most of the world's oceans are light limited permanently. But most of the world's oceans where there is enough light for photosynthesis are also limited by nutrients to some extent. And the more productive regions of the world's oceans are going to be those areas where there's some mechanism to bring those nutrients back up into the photosynth and make them available for use. So, nutrients tend to sink out of the system. And when they do, they are now removed from the area where there's enough light. So you can look at it visually like this. Where there's enough light, it's a light blue band. And you can see our active phytoplankton there. Right? Photosynthesizing along, life is good. Right? We're kind of in a photosynthetic nirvana. But they die, they sink, they start to decompose, and by the time they're broken down into their constituent parts that can be reused, they're now down in the dark blue stuff, where there's no light. Can't be used for nutrients. Plenty of nutrients, no light. The two are sort of in sync. So, if you look at the world's oceans and where you have high productivity, this is something we looked at briefly, the dark green areas are not arranged in any kind of latitudinal pattern like biomes were. You can't just go north and south from the equator and make sense of it. But what you can start to notice is that the majority of the productive regions are in shallow water. And also in certain areas of the ocean where other processes that we'll talk about operate that bring that deep nutrient-rich water back to the surface and allow for it to be used where there's life. And one such mechanism happens right off the coast here in California. That's why we have all this marine productivity here. Big California, huge schools of sardines and anchovies. How many of you read Cannery Row? Right? Okay. Really? One person. 2, 3. Right? Really? All right. That's going to be the assignment for final. Read Cannery Row. A quick report. Good book. Don't watch the movie. So, what we have here in California is the wind blows in a certain way, and if you take a course in oceanography, you'll learn all about this, and pushes the surface water. But, of course, the Earth is spinning, right? Newsflash, the Earth is spinning. And first, if the Earth would suddenly stop spinning right now, we'd all go flying forward at 2,500 miles an hour. That would be a trip. For about 10 microseconds, we would be recycled into nutrients. But because the Earth's spinning, it causes things to bend. Well, do you know what that's called? Coriolis force, right? And it bends to the right in the northern hemisphere and to the left in the southern hemisphere. So that surface water being pushed by the wind bends. And it bends offshore. And when it flows offshore, it's got to be replaced. But there's no water next to it to flow out to replace it. There's only land. So where's the water come from? It's pulled up and down deep to replace it.
Now that deep water that comes up to the surface, full of nutrients. And when it comes up to the surface, it's now in the photic zone, and it can support high levels of productivity. We call that uprun. That's why the water's so dang cold here, because it's being sucked up from down deep, where it's cold. So it's very productive, and you can see that there are major upwelling zones in North America, South America, and North and South, the west coast of North and South Africa. These are all very rich, productive upwelling zones. And back in that graphic where I told you all those different biomes, upwelling zones were in there. They're less than 1/10 of 1% of the world's surface area, but they account for about 50% of the world's fish catch. So they're extremely productive habitats. There are other areas that are productive. All these shallow bodies of water here are very productive. Why? Because they're shallow enough for the big storms and waves to suspend and mix the water from down deep and bring it up, roil it up, and resuspend the nutrients, right? And you bring those nutrients back up and make them available. So, for instance, up here, right, Bering Sea, right, made famous by Deadliest Catch, right? How many of you watched the Deadliest Catch? Okay, all right. You know, I was into it for a while, but there comes a point where you just can't watch another crab pot go over the boat. Get excited about what comes out, right? But I'm sure it's exciting if you're up there. Well, that's a very productive body of water because it's shallow. It happens to be where gray whales go to feed in the summer, right? Because it's so productive that the bottom's full of these great big amphipods, these little crustaceans that they eat. Okay, so that's where they go to get a meal. Other places like the North Sea, very traditionally rich fishing grounds. Shallow continental shelves. These are all productive areas. And then there are certain areas like the equator of the eastern tropical Pacific and regions off of Antarctica where different phenomena come, where water is either sinking and water's coming up to replace it because it's cold and bringing up nutrients, or water is being blown in opposite directions on either side of the equator, and it's kind of doing this, and sucking water up. So one of the world's biggest tuna fisheries is all here in the eastern tropical Pacific. Right? So if you buy a can of tuna, probably comes from somewhere around there. It was caught there. And the reason all that tuna can live there is because there's high productivity, because we have what's called equatorial upwelling current. So when we look at the world's oceans, when we see high productivity, there's some mechanism that bringing nutrients back up to the surface and making them available in the photosynthesis to promote high levels of production. And big areas of the world's oceans that are very low in productivity, the open ocean basins, have no mechanism to bring those nutrients down. So the surface water where there's enough life are very low in nutrients. Yeah?
Why is it measured in carbon per square?
Because
per
a measure of photosynthetic activity is how much carbon dioxide is fixed into organic molecules. That's what the process of photosynthesis does. All right. So, we're going to continue this discussion of nutrient cycling in the context of another property of ecosystems, and that's this thing called biogeochemical cycles. This gets more, we've talked a lot about how energy flows through ecosystems in these food chains and food webs, right? So we've got the yin covered, right? But now it's time to do the yang, right? So we did energy, now we're going to do matter. So we're going to talk about how matter cycles in ecosystems. And we characterize these cycles in these things called biogeochemical cycles. So it's almost like I knew I was going to say. Energy flows one way in an ecosystem. I have no idea what you mean. Matter cycles? Okay, matter cycles in ecosystems. And what are we talking about? What kind of matter? What kind of matter matters? So to speak. Well, there's a expression called CHOPS. How many of you heard of CHOPS? Right? The molecules of life, the atoms of life. Carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. These are the main atoms that go into the building blocks of biological molecules. There are other ones, to be sure, in small amounts, but these are the bulk of these molecules, use these atoms. So you have things like calcium. We have a lot of calcium in this too, right? For all those bones we have.
Other things are in trace amounts, things like iron and gold and other precious metals. In fact, when I was in your position, I think the average precious metal value of a human body was like $1.87. It's probably closer to $5 or $6 now with inflation, right? But I was very comforted by that fact because every time you have some relative that say you'll never amount to anything, right? And you go and say, "Oh, contraire. On the market right now, I'm worth $1.87." Right? So, don't ever let anyone tell you you're not in control. All right, so these are the building blocks, and this is the matter that cycles. It builds up into molecules and it gets broken back down into simpler ones. These are the building blocks. If you were, my 2 5-year-old boys are just insanely into Lego. Right? Okay? So these are the Lego pieces, right? You build them up into, the Millennium Falcon, and then they get broken down into, a pile of little pieces, right? And then good luck following the instructions, trying to do your sentence. And they're called biogeochemical cycles because it represents the different phases the matter can exist in. The bio stands for biotic. That's elements that are locked up in living molecules and living parts of organisms. So all of you constitute part of the bio in biogeochemical right now. The matter in you is what we refer to as biotic. Geo is geologic, so it's things like sands and rocks, geologic structures. And chemical is just small molecules that are freely dissolved in some medium, either the air, the water, or the soil. So matter can occur in any one of these 3 types of reservoirs for all of these different elements that we talked about: water, carbon, nitrogen, phosphorus, sulfur. Now, these cycles of this matter can be local in scope or global. So local cycles are best characterized by things like nutrient cycles, particularly in terrestrial ecosystems. Think about terrestrial ecosystems. When something dies or something relieves itself, where does the waste go? In a pre-indoor plumbing world, on the ground, right? Okay, and then there it is. It dies, it rots, decomposes, it's put back in the soil and reused by the organisms right there. Right? So it's a local cycle. It's got a very local scale to it. But some cycles are global. So I was just, I'm embarrassed to say this, but I was watching the Weather Channel. You get over a certain age, you can actually watch the Weather Channel. I'm sure there's some of you out there. I was trying to find MTV. Team Fred. Catch a half hour of that before our dash. It's the Weather Channel. We're talking about the water cycle. It's fascinating because the average residency of water in the air is about 10 or 11 days. And water is cycling all the time. And so the guy said, this struck me, that there may be water molecules in you that once resided in George Washington or Albert Einstein, okay? Or Charles Darwin. Okay? Could have used that water molecule about 4 weeks ago, right? So it's kind of tricky. Water moving all the time and going in different forms. And it really kind of blows your mind. Maybe like some substance to get there totally silly. So you think there's this huge interchange of stuff going on all the time. And these cycles can be global because water or some of these other elements can get up in the atmosphere and go all the way around the world in the jet stream. Okay? So it's kind of tricky. So again, this just drives home the point that the energy is flowing one way. It comes from most ecosystems, the original source, the sun, goes through all these different trophic levels, but eventually radiates out into the atmosphere as heat, never to be used again in ecosystems, right? In that manner. But the matter that's in all these things keeps cycling.
largely by the good action of decomposers, that when things die or when waste is removed, they break it down and put it back in the system in a form that can be reused. Now, what factors affect biogeochemical cycles? Because this would be very much in the wheelhouse of ecosystem ecology. You wouldn't just be concerned about studying organisms in the ecosystem, but you want to get a handle on these biogeochemical cycles and how matter is moving between one form and another, what we call flux rates. And you're budgeting the movement of matter. So, for instance, we're going to talk about global warming a little bit later today. Trying to figure out the rate at which carbon dioxide is released and reabsorbed is critical in trying to accurately model how quickly the Earth will warm. If you don't have a handle on these flux rates, you can never try and predict how the temperature of the Earth will change in time. So one of the factors you need to know is, first of all, you have to identify what are the different types of reserves, these biotic, chemical, and geo reserves. You have to identify all these different reserves, and there may be several forms of all of them, right? And how big are they? How much of that element, total element budget, resides at any one time in these different reserves? Right? So it'd be kind of like, doing a inventory of your assets, right? I don't know, that would actually be very simple in my case, but let's say you're Bill Gates, right? Okay, we were trying to inventory his assets. Well, he'd have money in all kinds of different categories: stocks, bonds, offshore accounts, mattress under the mattress, and so you have to identify where all the different pools of money were and how big they were. That would be analogous to what you would do in biogeochemistry. But then you need to know how it moves from one reserve to the other. What's the rate at which it goes from, let's say, carbon dioxide locked up, or carbon locked up in biological molecules, to carbon dioxide released into the atmosphere? And what's the rate at which carbon dioxide in the atmosphere is drawn down either into phytoplankton in the ocean or plants photosynthesizing in the earth? Or how quickly carbon locked up in the vast reserves of hydrocarbons that have existed on this planet is being converted and released back into the atmosphere as CO2. Well, for millions and millions of years, it was a very slow flux rate, and then along came Homo sapiens and figured out that we could use this stuff to propel ourselves around in vehicles, and all of a sudden that rate changed dramatically. Right? We started releasing carbon dioxide at a much higher rate from that particular reservoir. And then the last thing you need to know is, how does one cycle affect the other? And we're living right through this in California right now, right? What are we experiencing in California? A drought, right? Why? Well, it has to do with temperature and heating patterns, okay? Which is being affected by carbon dioxide, right? And maybe we've influenced that process and changed it. And part of it's natural. So the carbon cycle will affect the water cycle, and it'll also be affected by other cycles, the nitrogen cycle, the sulfur cycle. So these cycles interact with each other and influence them. Okay, so you have to know how different cycles influence the movement and flux in other cycles. All right, so let's start with more local cycles. Talk about nutrient cycles. What are nutrients? Let's just get that out there so we understand what we're talking about. Well, all photosynthetic organisms have certain needs that they must achieve, and I love this word, constitutively. We use that for defense, right? But when you achieve something constitutively, you do it through your diet, right? So they are a source of nitrogen, a source of phosphorus, what you commonly know as fertilizer, right? So when you put bat guano or horse manure or anything else like that in the soil, you are increasing the nitrogen and phosphorus content in the soil by mixing that in. But they also need a source of vitamins. There are certain key vitamins plants need that they can't produce themselves. They get from bacteria that produce them. So these vitamins are obtained from the external environment. And then all plants need a source of what are called trace metals. These are metals they need in extremely small quantities, right? But without them, it's a no-go. So we're talking about things like iron, copper, manganese, molybdenum, things you need in very, very small amounts, but are a vital role in the molecules plants manufacture for photosynthesis. We'll see how iron is one example of that in a very neat experiment. So, these are what nutrients are. And nutrients are formed when living tissue is broken down back into inorganic forms, into their constituent parts. They're also formed in certain cases. For instance, a nitrogen source of nutrients can be formed by taking inorganic nitrogen gas, and certain bacteria can convert that into nitrite or nitrate, which is more plants can use for their nitrogen. So there are different ways that these nutrients can be formed, but they cycle between being incorporated into the living tissue and being available in the nutrient pool, which is usually chemical nutrients dissolved in the water, in the soil, or floating around in the air. And who's doing this recycling? It's the decomposers. That's their key function in the ecosystem. That's the great role, the service they provide to the ecosystem. All right. Now, there's a fundamental difference in these nutrient cycles between terrestrial and aquatic ecosystems. And we've already indicated what's the driver of this difference, right? The presence of a catchment system in terrestrial ecosystems, the soil, which tends to retain the nutrients locally, and the absence of such a catchment system in aquatic ecosystems, where you tend to lose those nutrients from the system. So if we take a typical terrestrial ecosystem, here's a deer, it's consuming plant material, leaving little deer berries in your front yard after it's eaten your expensive landscaping, okay? Which is still got waste in it that will be broken down, recycled, and eventually it by, as with the tree it was feeding on, and that will all contribute to the detritus pool. It's dead material, it's dead organic material, which will be the basis for the decomposers to attack and break down. So all that material will enter the decomposing food web, and they will recycle that material back into the soil nutrient pool and make it available for new plants to use in the process. So it's a very local, somewhat closed system, thanks to the soil acting as a catchment. And here's an example of this material in action. So you can look at a boreal forest, biome, you can familiar with that. And you go and walk through the woods here. This isn't exactly boreal, but it's got many similarities to boreal biomes. You can see the place is littered with dead plant material. Logs, rotting logs, and leaf litter, and needles from conifer trees. But if you walk around the forest of a tropical rainforest, and how many of you walk around inside a tropical rainforest, you find there's a lot less leaf litter. And you might say, wow, what's the conclusion? There's a lot less productivity there, right? No, not productivity. It has to do with the fact that it's warm and it's wet there, and it's not nearly as warm or as wet there. So things decompose very fast in rainforests. These nutrients are recycled very quickly. It's a slower process in higher latitude forests. So you really don't want to lie down and take a long nap on the floor of the rainforest floor, because you just might wake up and recycle. Now, it's not to say that nutrients can't be lost in terrestrial systems, and we have had an active hand in promoting this in many ways. So one of the roles vegetation has is it helps to hold onto the soil and retain the soil and act as a mechanism of holding on to those nutrients. And you can see this in an experiment where you take two different watersheds, one that's forested, one that used to be forested, and you cut it down. And you sit down there and you control and you collect the water flowing out of these catchment systems. And you measure the nutrient load in the water, how much nutrients are being flushed out of that system in the rivers draining through it. You find, in fact, that the devegetated plot has a much higher amount of nutrients in the water than the vegetated plot. Why? because all of that's leaching right into the water and being flushed out of the system. So devegetation can promote nutrient loss from the system. And so that's why, one of the functions that plants serve in a system is their roots help hold on to the soil and prevent nutrient loss from the system. Very important function they provide. So it's not, soil does have to retain nutrients, but it is possible for terrestrial ecosystems to lose their nutrients by advection, by loss, if they're disturbed or mechanisms that usually help retain those nutrients are disrupted by devegetation or fire or whatever. In the aquatic ecosystem, it's a very different story. So think back to that deer. When aquatic organisms die, or when they defecate, you might say, that's not like a deer, right? But in fact, fecal pellets are a big part of the export in the aquatic ecosystems. And, they tend to be small, they're not very noteworthy, although we have spent a lot of time in our research collecting whale poop, right? And that's a colossal thing. And it's not what you might think it is, right? It's very ephemeral. They like to let it go at the surface. There's something about whales, they like to poop on the surface, right? So they'll let one of these things go, and then it'll start dissipating out and sinking, right? And so we kind of run up there and try and collect it as quickly as we can. Now, why are we collecting whale poop? Well, that's another story. But you can tell a lot about what whales are eating by collecting its poop. So I highly recommend it if you've never tried it. But anyhow, yes, dead things and waste things. And by the time they break down, they're out of the light and they can no longer be used. So how are nutrients recycled into the photozone, the aquatic ecosystem? Well, this is one such mechanism. That would be one way you could bring those nutrients back up to the surface. If you have some sort of a oceanographic phenomena that forces deep water back up to the surface, that brings nutrients back into the photozone and makes it available for photosynthesis. Lakes have their own way of doing that. So, for instance, in lakes, how many of you have lived by a lake in temperate latitudes that freezes in the winter, and some few of you have? So what happens is, start off in the spring. In the spring, you have a lot of wind, and the cold water on the surface is still sinking, and so the lake is mixing, because cold water is sinking, and the wind is agitating it, stirring it up, right? So the lake becomes well mixed, so the nutrients down deep in the aphotozone are brought up to the surface, and you have a great big phytoplankton bloom in the spring. By the summer, when it gets warmer, the surface water gets warmed up. It actually becomes less dense, and it floats on top of the denser, colder bottom layer. And the lake becomes stratified. And so now anything that sinks down to the bottom water stays down. So the nutrient supply gets used up in the surface water, and it builds up in the deep water. And the phytoplankton bloom dies, and you have nice clear water again in the summer in these lakes, in deep lakes. Then, in the fall, it starts to get colder, the surface water gets heavier, the wind ruffles it up, it sinks, the lake gets mixed up again, and there's still enough light to promote a fall phytoplankton bloom. So there's another resuspension of the nutrients in the fall. And then by the winter, the lake freezes, the surface waters are the coldest, they sink, and they're constantly being mixed, but it's too cold and too dim to allow for much phytoplankton growth. So the nutrient level becomes uniformly distributed, and it's not used in the winter, but it's ready to take off when the light returns in the spring. So there is a seasonal cycle in temperate lakes for nutrient supply to the surface. That could be another example of nutrient cycles in aquatic ecosystems. So if we look at this global distribution of productivity in the world's oceans, we can recognize that, like we said before, wherever we see high productivity, there's some mechanism for nutrient supply back to the surface, either by mixing in shallow water, by storms and large waves or currents. Sometimes you can have equatorial upwelling, in which waters are diverging at the equator and the deep water is coming up. You can have coastal upwelling in places like Africa and North and South America. Here you have cold water sinking and causing deep water to come up to replace it in Antarctic water. So there's all kinds bringing nutrients to the surface. But wherever you see high productivity in the ocean, it means there's some mechanism that are bringing nutrients and keeping them at high levels in the photosynthesis that they can be used. Okay, which brings us to an interesting experiment. And I love this graphic because, once again, it's not your textbook, because I get you totally wrong in terms of how it's done. But don't try and read this. I'll walk you through it, and then I'll point you back to the relevant parts. About, what was it, 69, so 69, 44 years ago. That was a lot. Okay, 44 years ago, a guy by the name of John Markey, who used to be the director of Moss Landing Marine Labs, just down the road. He was a physical oceanographer, physical/chemical oceanographer. He said, you know what? We can explain a lot about the world's oceans, where you have phytoplankton in high amounts and where you don't, just based on the nutrients. But there are areas of the world's oceans where if you go there, you find a lot of nitrates and phosphates, high levels of nitrates and phosphates, and you would think that should support high levels of phytoplankton growth, but you don't see high phytoplankton growth. So what is it about these nutrient replete areas, macronutrients, we call them nitrogen, phosphate, big nutrients, macronutrients, that is keeping the production low? And he said, the one thing all these places have in common is that they are very far from any source of iron. Because where does iron come from?
Land.
Rocks, right? The erosion of rocks, right? Which is mostly land. So rivers and whatnot, dumping sediment out in the ocean, that's a source of iron. Where are the nearest rocks in the open ocean? 10,000 feet down. No way of getting iron up to the surface. So these areas are iron poor, iron depleted, nutrient replete, iron depleted. And he hypothesized all you would have to do is throw some iron into these areas and you could create a phytoplankton. Just add iron, right? Instant phytoplankton. And he was able to convince NSF to fund the first of many Iron experiments, where they went with ships, not helicopters. You can fly a helicopter 2,500 miles into the middle of the Pacific Ocean and start dumping iron out the door, right? So they had great big ships that steamed back and forth, and they dumped iron dust, iron filings, iron dust out the back of these ships, and they laced a section of the ocean with iron. That's all they did. And they sat there and they waited and they saw what happened. And sure enough, what happened was, in the area inside, on the surface, the chlorophyll level exploded. And the chlorophyll level is an indication of phytoplankton. A huge phytoplankton bloom occurred where you put the iron. Now, inside the area down at 30 meters, you didn't have phytoplankton bloom. Why not?
No light.
No light. Too deep for light. Okay, light limited. Right? Outside the bloom, very low levels of phytoplankton, no iron. Right? And so they said these areas are just iron limited. And here's some pictures. That's what it looked like before they put the iron in the water. Look at that color of the blue water. That's what it looked like 6 days after they put the iron in the water. That's all they did. Add some iron in the water. And here's some water outside the patch and inside the patch at the height of the bloom. Right? And so they proved this hypothesis is that huge sections of the world's oceans have low productivity for one reason and one reason only, because they're limited in their iron. This tiny little component necessary for photosynthesis. But again, it's one of those things, the weakest link. All you got to do is be lacking one part, and it doesn't work. So think about a car. Think about all the parts that have to work to make a car run. Okay, now just take the spark plugs out of that car. If you had that car on your back, right, before you remove the spark plugs and after you remove the spark plugs, could you think you could notice the difference in the crushing weight that was, on your back?
No.
No. But one car would start and run and the other wouldn't. It would just be the little spark plugs you removed that stopped it from running. So the iron is like the spark plug. Very small part of the car, but an essential part for it to work. Right? So people thought, great, wow, fantastic. We can go around, take our junk cars, grind them up, dump them in the ocean, and create huge phytoplankton blooms everywhere, right? And that's going to draw down CO2. So maybe we can do this to draw down CO2 in the atmosphere. Increase productivity in the oceans and draw down CO2 to solve the global warming crisis. All one fell swoop. You know? Well, there's a problem. A problem of unintended consequences. Because what's going to happen as soon as the iron's used up or sinks? Bioplankton's going to die. And they're going to die, and there's going to be a whole bunch more than there usually is. And that's going to start sinking, and that's going to start decomposing very rapidly. And you know what it's going to make? Methane. And methane bubbles up, goes in the atmosphere, and guess what? Methane has one carbon, CO2 has one carbon, but methane is 20 times more powerful as a greenhouse gas than carbon dioxide is. So you might just actually exacerbate the problem by doing this rather than solve it. We have a good history with this, right? 2 words, cane toads. Right? One word, kudzu. Anyone from the southeast? No? Go to the southeast, ask someone about kudzu and whether they wish they hadn't introduced it back in the 30s. Right? It's overgrowing everything. Okay, so that's nutrient cycles. What about global cycles? Well, like I said, they're broad in scale, hence the word global. And in almost every case, one aspect of these cycles involves some exchange between the atmosphere and the rest of the ecosystem. So there is an atmospheric component to these cycles. And once you have an atmospheric component, there's no limit to where you'll go on here. If you get up in the atmosphere, you can go anywhere. And that was proved very handily recently by several people who have managed to successfully circumnavigate the globe in a balloon, right? They went up in a balloon, they caught the right currents, and they went all the way around the world. It was always a challenge. Yes?
How long did it take?
No, I'm not sure, but 10 days or something like that. Not that long.
75 to 90.
75 to 90 days?
Around the world in 80 days.
Well, that was
of the
Phineas Fogg.
Yeah, I know.
Okay, he was in boats and ships. He wasn't floating around in a balloon. I think it's a little faster when you get up in the jet stream. But I don't know the answer to that. That would be that's something that probably be Wikipedia.
I think 10 is stretch.
Huh?
I think 10 is
10 stretch? Well, the challenge has been laid down then, hasn't it? We could be better. The exception is phosphorus. There's no atmospheric component of phosphorus. And so phosphorus is actually it's a big crisis out there. Phosphorus is rapidly becoming limited. And it's getting harder and harder to create enough phosphate to support the high levels of agriculture that the plant demands to feed itself. So it's a bit of an issue beyond scope of this stuff. And basically what this does is unites all the ecosystems on the planet into a giant interconnected biosphere. There's nowhere to hide. There's nowhere you'll be safe from the influence of the rest of the world. Yeah. Think back just a year ago now, Fukushima, right? It wasn't only a matter of days when radiation levels started increasing here in California. Okay? So there's no place in the earth that is completely isolated from the influence of other ecosystems. It eventually can get there. So the general idea behind these biogeochemical cycles is that you've got all these different types of reservoirs, living organisms, nutrients, soil and sediments, rocks, lava, fresh water, oceans, the evaporation, and there's movement by varying mechanisms. Evaporation, precipitation, transpiration, sedimentation, tectonic processes, volcanic eruptions, biological processes that are constantly moving these elements from one reservoir to another. So they're cycling. And if they get up in the atmosphere, they can really travel far. And so there are several different cycles that have been identified. Here's the nitrogen cycle. So here's that nitrogen occurs in lots of different states. There's a huge reservoir of it as atmospheric N2, nitrogen gas. 80% of our atmosphere is nitrogen gas. So there's a lot of nitrogen there. But it moves back and forth from that form to things like nitrate, nitrite, ammonia through biological and natural processes. So, for instance, certain organisms can take nitrogen and fix it, convert it from nitrogen gas to nitrogen. Bacteria can do that. It occurs in the ocean. It occurs to a much greater extent in land ecosystems, where plants that have these nodules full of nitrogen-fixing bacteria exist to accelerate that process. But also the nitrate, and NH4 can be denitrified, converted back to nitrogen gas, which goes back up in the atmosphere. You can have, of course, nitrates running off in streams and rivers and accumulating in the ocean. And it can also break down and be incorporated into sediments and rocks in the deep sea and in the geology. So there are varying forms of nitrogen that move back and forth between geologic, chemical, and biological reservoirs on a global scale. And this particular cycle has an atmospheric component. So both nitrate, nitrite, ammonia, and nitrogen gas can move in the atmosphere. The phosphorus cycle doesn't have an atmospheric component. So it has a bio and a geo and a chemical reservoir. It's just the chemical reservoir doesn't include a form in the atmosphere. So phosphate moves back and forth between rocks and the chemical reservoir in the soil to the biological reservoir in plants and animals on the land, or to lakes, rivers, or the ocean, and to plants and animals in the aquatic ecosystem. But there's no form of phosphorus that moves in the atmosphere. So it's much more constrained in its ability to move around through the growth. Here's the water cycle. So water exists in three phases: ice, liquid water, and water vapor. And so there's a ton of water in the atmosphere. And it gets in there by evaporation, and it comes out of the atmosphere back out into the land or the water by precipitation. Some of that water that comes up, you can see that about 319 gigatons of water evaporates over the world's oceans. Only 283 of those fall back into the oceans. So the oceans are constantly supplying the land with a source of water. It evaporates from the water into the atmosphere as it comes onto the land, usually rising up over mountains, it cools and drops that rain on the land. So the oceans are subsidizing our fresh water. While it's over that atmosphere, you can see that it collects in the ground. There are aquifers and reservoirs underground. There's lakes and streams and other wetlands that hold that fresh water. And there's a huge amount of that water held up in living biological tissue. All of that will move eventually back either through runoff or evaporation and cycle back to the other components of the system. So that was the water cycle. Here's the CO2 cycle. So again, CO2 can occur in the geologic formation down up in rocks, carbonate minerals in rocks. It can be in the form of fossil fuels, which are carbon-rich reservoirs. They have high amounts of carbon associated with them. They can occur dissolved in the chemical form in the atmosphere, in the soil, or in the water. And it's locked up and bound up in terrestrial and aquatic organisms as well. In terms of their molecules. Yes? Numbers are the sizes of the reservoirs, and in parentheses, when you have arrows, it's telling you the amount that's moving in flux in that direction. So you can see that more carbon dioxide is released to the atmosphere that is drawn down in the shallow oceans. Right? But the net drawdown of oceans is a net sink. But the most interesting thing about this graphic is what is the single largest source, reservoir, of carbon on this planet? Fossil fuels, 25 million gigatons, right? And for millions of years, it was a fairly inert, low-flux reservoir that sequestered carbon very effectively in the Earth's in the Earth. And then we figured out we could refine it and use it to do things. We release that energy And so the flux from this reservoir has increased dramatically since about the middle of the 1800s. Right? We have altered the biogeochemical cycle dramatically through our actions. We've taken the largest reservoir and dramatically increased the flux rate by which that carbon is released into the atmosphere in the form of CO2. And we can see this effect. So here is carbon concentrations in the atmosphere. By the way, we just passed a milestone. Did you know what that is? This is data information. 400, baby. 400 ppm. We are now at 400 parts per million CO2 in the atmosphere. We cracked the 400 ceiling. And you can see that since 1960, the steady rise in carbon dioxide. Right? But you can also see there's a seasonal cycle. This is from Mauna Kea, the observatory in optical light. So it's in the northern hemisphere. It's in the tropics, but it's still far enough from the tropics that it experiences some seasonal cycles. And you can see that, in fact, CO2 is lower in the summer and higher in the fall, because in the summer, with light and warm temperatures, there's more photosynthesis drawing down the CO2. When the winter is cooler, there's less photosynthesis. And so there's this natural seasonal cycle. But you can see the trend is dramatic, right? It's increasing. But that trend is boring compared to the next one. That's since 1960 to 2005. Check this one. Now, how do we have CO2 levels from 1400? Fossils?
Well, I mean, ice cores.
Ice cores, very good, yeah. They're fossil bubbles, right? So when ice forms, bubbles are caught in the ice. And they're bubbles of the air at the atmosphere at the time. And some of these ice cores are hundreds of years old. The ice in these cores are hundreds of years old. So you liberate the bubble in that ice and sample the relative portion of gases, and you can determine what the CO2 concentration was in the atmosphere at that time. Yeah?
At 1600, is that close to zero, or is that only like 240?
That's about 240. That doesn't go to zero. Right? If you did to zero, it would have less. It would be less than that. We want drama, right? So, what you can see is for hundreds of years, the CO2 level remained relatively stable. Back in the good old years when all those fossil fuels were still locked up in that 25 million gigaton reservoir. Then right about 1850, we started drilling and releasing that stuff, right? And the rate at which we did that started accelerating, and so look what happened to the concentration of CO2. It's skyrocketed. Out of control. So it's up at 400 parts per million now. We cracked the 400 threshold for the first time ever since we started recording these things. So why do you care? Why is CO2 a greenhouse gas? Well, the way CO2 works is this. Sunlight hits the surface of the earth, and a lot of the energy bounces off and goes back into space. So that energy is not absorbed. And it's particularly likely to bounce off of light-colored surfaces. That's why they're light. All the light's reflecting black. Ice and snow is very good at reflecting light. Water is not so good at reflecting light. It tends to absorb the light, absorb the energy. Now that light that bounces back up goes out into space. But some of that light that's absorbed is absorbed and then re-released as longer wavelength infrared radiation. And that thing starts radiating out into space. But that stuff will bounce off of greenhouse gases, just like it will bounce off the glass panes of the greenhouse. And it will trap it inside that area. And so the more greenhouse gases you have in the atmosphere, the more it holds onto that long-range radiation. It keeps it from radiating out to space. And so the temperature goes up. The same reason it goes up in the greenhouse. And CO2 is one such gas. Methane is another such gas. There are other ones as well. And it's kind of a two-edged sword, because the warmer it gets, then the more ice and snow melts. The more that ice and snow melts, the less of the light gets reflected off, the more of it gets absorbed, And the more long-range radiation is then released to bounce back off the increasing greenhouse gases, and it turns into a positive feedback loop. Now they say that something like this might have been going on another planet nearby, a planet called Venus. And eventually scales tip and you have what's called the runaway greenhouse effect. And now Venus is the hottest planet of the whole solar system on the surface. Yes, it's hotter on the surface of Venus than it is on the surface of Mercury. And it's got an atmosphere of opaque, impenetrable sulfuric acid, which keeps anything from escaping that atmosphere. So, sounds like quite a big issue. You can see some of the properties of greenhouse gases. Carbon dioxide has about 50 to 200 year residence time in the atmosphere, and it's got a greenhouse warming potential. It's the standard of 1. When you compare all of the greenhouse gases to the potential of CO2, you can see methane, fortunately, it's much shorter lived, but it's got a greenhouse warming potential of 21. So trading CO2 for methane might not be a good anti-global warming strategy. And eating lots of burritos probably isn't another good thing. Nitrous oxide, okay, for those of you who like to sneak into supermarkets and puff the top with whipped cream. Don't do that. Because it's got 114 year residence time. It's got a 289 global warming potential. Fortunately, it's very rare. It'd be interesting in nitrous oxide. Very funny. You might be in trouble if you all the black hat. Okay, what's one of the consequences of global warming? Well, rising temperature is one, but it's not the only one. In fact, it's not the most immediate. Already, we are experiencing acidification of aquatic ecosystems because CO2 is in this unique flux with the water. It dissolves in water. When it dissolves in water, it becomes carbonic acid, which dissociates into bicarbonate and hydrogen ions, which increases the pH of water. So the more CO2 dissolved in water, the more acidic it becomes. And we can see that lakes that become increasingly more acidic become much more inhospitable to species living in that water. You see that fish diversity in lakes is directly related to pH of those lakes. Acidic lakes have fewer species. More normal pH lakes in the 7 to 8 range have much higher species diversity. But it's not just lakes. It's the ocean. So here's the, I want to ask you about this. Here's the ocean chemistry involved in how when CO2 gets dissolved in seawater, there is a very intricate carbon chemical reaction. And the result is that this particular ion, the carbonate ion, is drawn and blocked up. So you remove this stuff from the ocean. And this is very important because this is what organisms use to create calcium carbonate. So when the oceans become more acidic, we're not talking about much. We're talking about a very, very small change in the pH. You can see the amount of this carbonate ion that becomes available declines dramatically at high CO2 concentrations in the atmosphere. And what does that mean? Anything that builds a shell or an exoskeleton out of calcium carbonate has a harder time doing it. Corals, certain plankton species. And so this has tremendous implications for coral reefs and phytoplankton species and even some zooplankton species worldwide. It's already happening. And it's not a huge, it's not like you stick your hand in this water and it starts dissolving because it's so acidic. We're talking about maybe a couple of tenths of a pH point. So small you wouldn't notice it yourself. But small, those of you who take chemistry, you know that small changes in pH can drastically alter the reaction equilibriums of chemical reactions. And that's exactly what's happening in the world ocean. And so it's having dramatic impacts on oceans, and some models estimate that in 50 years, most of the coral reefs worldwide will be gone because of ocean acidification. If you're putting off that trip to the tropics, I think it is pretty soon. Check out the coral reefs. And you can see how the pH of the overall oceans have changed over the last several decades. This is the change in sea surface. So anything red or orange means a decrease in pH. And the more red or orange, so you can see that parts of the Atlantic and the Northern Pacific and the Southern Ocean have dramatically acidified over the last few years. And these are the kinds of things that are affecting corals, and there are lots of calcareous species of plankton. Some of them are very key phytoplankton species that are at the center of marine food webs in high latitude oceanic ecosystems. And they're being affected. Okay, so that's a good place to, on this bright, optimistic